Welcome, students. Today we are going to do a review uh, of matrices for ODEs. All right. So note that this review is only for ODEs, and matrix as such cannot be, the theory of matrices cannot be combined in one lecture. So what we're going to study here is matrices, how they correspond to the system of linear equations, and their linear independence of the solutions and eigenvalues and eigenvectors of the matrices, of square matrices. So matrices were invented long time ago, all right? But it was formalized in 1850 by James Sylvester, and it was used for solving algebraic, linear algebraic equations. Okay. So first of all, what is a matrix? So the notation, so matrix is essentially a rectangular array of numbers. So you will have, say, A11, A12. We have to write them in a special form so that the representation is nice. We know which, we give them subscripts so that we know where they exactly lie in the array. A21, A2n, and then this array can go on. So AM1, AMN. So this is an M cross N matrix with M rows and N columns. Yeah. And what are these entries? So AIJs belong to C. They are complex numbers in our case. Okay. Now, if you have a system of linear equation, say AX plus 3Y equals to 1, say 4X plus 5Y equals to 2, then this system of equation can be written in the following form. You would have already seen this in a linear algebra course or even before. Yeah. So they're very powerful tools to solve linear equations, system of linear equations, but not only that, they go way beyond. So typically, matrix in your textbook will be a boldface and written in capital. Here, when you write Aij, this represents the row number and this represents the column number, right? So another notation for a matrix is A can be written as Aij or Aij M cross N. Yeah, so these are your rows and these are your columns, right? All right, so now you can have a row vector. So if a matrix of form, so if you just consider this matrix, just this part here, you get a row vector, all right? So a row vector or row matrix, row vector is 1 cross n matrix, right? Basically given by A11, A12, n, and a column vector is is in this case we have say m cross 1 matrix, a 1 1, a 2 1, a m 1, right? So these are the row and column vectors of particular dimension. Now we want to talk about certain property of matrices, particularly when do we say two matrices are equal. So equality, so given matrix A, m cross n, and B, so I'm using this notation for matrix. Note that if matrices do not have same number of rows or in columns, they can't be equal. So the number of columns and number of rows should be equal for the first criteria. Second is that A is equal to B if Aij is equal to Bij. That means the corresponding ij's entries should be equal for all I and j. Yeah. So this, similarly, we can define A plus or minus B to be the matrix obtained by adding the corresponding entries in the matrix. Again, the addition is only defined if the matrix have same dimension. That means they have same number of rows and same number of columns. Now multiplication by a scalar. So let alpha belong to C, a complex number, then alpha A is defined to be alpha Aij. That means you are multiplying each entry of the matrix by alpha. Okay. Also note that minus A is a notation for minus 1 times A, which is same as Aij. Now matrix multiplication. The matrix multiplication, two matrices can be only multiplied if they are of special kind. So you have A m cross n be a matrix, and B P cross Q be another matrix, or P cross R be another matrix. We can find product of these two matrices AB only if what n equals to P. Okay, so these two things should match. This should be equal. Yeah. Similarly, we can define BA to define BA only if what? Only if we have R is equal to M. So this is the first condition to be able to multiply two matrices. Now let's see how does the product looks like. So suppose now I have two matrices. So A M cross N and B N cross R are given, then C equals to AB is given by Cij matrix whose dimension would be M cross R. So the dimension of the product is going to be number of rows is M, number of columns is R, is given by. So I'll write down the entry. How will Cij look like? So Cij is summation k going from 1 to n, A I k b k j. So this is how you define product of two matrices. So note that because of this, you see that AB has dimension. So AB has dimension what? AB has dimension. If you go back here, AB is an M cross R matrix, whereas BA is an what? In this case, BA is going to be P cross M matrix. Right? I mean, provided these products are defined, right? So I should not write them. I should write these separately here. So therefore, AB is not even equal to BA, even if the product is defined. So the first obstruction is that the product may not be defined because the mismatch of number of rows and columns. But however, even if the product is defined, their dimensions will be different. Right? So identity matrix. So what is an identity matrix? So identity matrix is given by I, which is basically on principal diagonal, you have 1. Everywhere else, you have zeros. The idea behind a matrix is that AI is equal to IA. Yeah, so suppose I is if I is an n cross n identity matrix, and A is n cross n matrix, any n cross n matrix, then AI equals to IA. Now, inverse of a square matrix. So inverse only exists for square matrix. So this concept is defined only for square matrices. And even for square matrices, the inverse may not exist, but at least the concept requires you to have a square matrix. So A is invertible or non-singular. So A n cross n is singular or non if there exists B n cross n such that AB equals to BA equals to identity. And we call B is equal to A inverse. Okay, so A is non-singular if and only if determinant of A is non-zero. Yeah, and A is singular if and only if determinant of A is zero. So A is non-invertible, that's what, right? Because invertible and non-singular, we are considering them to be the same here. All right. Now note that this is only valid, these kind of equalities are only valid for an n by n matrix. Now if the dimension goes, if the n goes to infinity, if we talk about an infinite dimensional matrix, then things will change. Okay, so we were not considering those things here. Now, how can you compute the inverse? So if you have AI, you can use Gaussian elimination. If you apply Gaussian elimination, you will get A inverse. Okay, so you should see page 291 of Boy's diploma. The next thing we want to discuss is a transpose. So what is a transpose? So A transpose is transpose of matrix A obtained by interchanging the rows and columns. For example, if you have A equals to Aij m cross n, then A transpose is going to be Aji n cross n. Yeah, the dimension will also change. For example, let me digress a bit more here. If A equals to 1, 2, 3, 4, 5, 6, then A transpose is the rows become columns and the columns become row. So you get, this is your A transpose. Now is a discussion about the conjugate transpose. So if you're given A, now A is a complex matrix, right? I mean, you could talk about conjugates of complex numbers. So that concept has been extended to the matrices. So suppose you have A, which is Aij, then A conjugate is given by Aij. Each entry is conjugated. So for example, if you have 2, 1 plus 2i, the conjugate is 1 minus 2i. So you change the sign of the complex part. So A bar is the conjugate. And what do we get? And we get A star is, you take the conjugate and you transpose it. So you get conjugate transpose. This is the conjugate transpose. So for example, let's see. So if we have matrix A, which is 1 plus 2i, 2 minus I, minus 1 plus 4i, 4, then A star is, so basically you have to make the rows to a column and conjugate them. So you'll get this bar minus 1 plus 4i bar, 2 minus I bar, 4 bar, and that is 1 minus 2i, minus 1 minus 4i, 2 plus I, and 4 conjugate is 4 itself. Now, vector multiplication, so we can take a matrix and multiply it by a vector. But before that, let's see if you have, want to talk about dot product. So you have matrix X, which is also a column vector. So now note that sometimes you can use for matrices as well. You can either use this round long bracket like that, or I use the square. I like to use the square ones. Let's just do this one as well. So these notations are same. Then we define X transpose Y is what you take. X transpose is going to be 1, 2, 3. And if you apply your matrix multiplication, you will see that this is going to be 4 times, so 4 plus 10 plus 18, which is going to be 32. Yeah. So X transpose Y can be written as summation I going from 1 to n, xi, yi. So this defines the dot product. Now we have the second one is a variation of this, a scalar or inner product. So scalar or inner product is defined generally as x, y of two matrices. So either you can use this notation, some textbook use this notation for scalar or inner product. This is simply summation I going from 1 to n, xi, yi, exactly same, but the extra part you have here is a bar on top. Yeah. Or in other words, you can say, well, this is same as X transpose Y bar. Yeah. Note that they capture a lot of, so why do we define these inner products? They capture a lot of physical aspect of your vectors. So for example, first of all, 1 equals to 2 when xi's and yi's belong to R. They are real, right? The entries of vectors are real, then they both correspond, they are equal. Otherwise, let's see. So what does, if they are real, let's see what does xx to the power half denotes. So xx is basically summation I going from 1 to n. You'll get xi square to the power half. And this denotes what? This denotes the the magnitude is the magnitude of vector x. Now, a few more properties of this, that only zero vector magnitude or length, or whatever you want to call it. So only zero vectors have length, only zero vectors. Now note, if xi belong to complex number, then what do we get? Then we have the problem, we have x transpose x equals to summation I going from 1 to n of xi square may not denote a real number, right? It may denote a complex number. Yeah. So therefore, which cannot represent length, right? So that's why to fix this problem, we define basically magnitude using the scalar inner product. So let me give you an example. So suppose our x is 1i, and then x transpose is going to be 1i, and then we get x transpose x is going to be 1i, which is going to be 1 plus I squared plus 1 square, which is 1 minus 1, which is 0. So you get a non-zero vector of length 0. So we should not define it like that, right? So the proper way to define it would be if you look at this one here, you'll get 1i, 1i, you get bar of this is 1 minus I, and when you do this, you get 1 square plus 1 square, which is 2. So therefore, it represents the proper, so it represents the length, right? So the idea is, if you look at the complex plane, you'll see that here you have 1, here you have I complex axis, and then this point will be still given by 1, 1, and you know that length of this part is, so length of this vector here is square root of 2, right? 1 square plus 1 square square root. So you see that the scalar product truly captures the length of the vector. Now we want to discuss the matrices and vectors of functions. So in this case, we have entries of our matrix, entries of matrices can be functions. For example, you have vector x, It will be function of a real variable mostly in our case. So we have x1 t, x2 t, xn t, or at with an arrow on top, or you can just write it in textbook. You'll see it with the boldface. This is going to be a11t, a12t, dot dot dot, a1nt, a21t, a22t, a2, amnt. Yeah. So matrix whose entries are basically, this matrix has entries as functions. Okay. Now, what does it mean by, so how do we extend the idea of continuity on an interval for either this column or this matrix? So for that, we have the following. We have xt or at is continuous, is defined to be continuous. All right, this is a definition, defined to be continuous on an interval I if every component, all right, if every component xit and aijt is continuous on I. Yeah, this is a very meaningful extension to have, right? That you have a matrix is continuous on an interval if every component is continuous on the interval. Similarly, we can define derivative and integral of a matrix. Derivative of a matrix dA by dt is going to be d of dt of aij. So you take each individual component and take the derivative of them. Similarly, integral a to b a of t dt is basically defined to be, take each component so now let's look at an example so that these things are clear. So example, let A be the following matrix: T, T square, T cube, T to the power 4. Then dA by dt, this as a matrix is derivative component wise. Derivative of this is 1. T cube is 3t square. T square is 2t and 4t cube. Right? And integral of at dt is integral of each component, which is going to be half t square plus c1, right? Because that's what the integral of this guy is, right? Right? Is half t plus c1. We'll get t cube, t to the power 4 by 3, 4 by 4 plus c2. Here we'll get t cubed by 3 c3 t to the power 4 by 4 plus, sorry, t to the power 5 by 5 plus c. Okay. All right. So now the further can be extended here. So we have d by dt of CA, where C is a scalar, C belongs to R, is C times dA by dt. And this is not equal to, yeah, this is a big caution, this is not equal to, yeah, where C is a constant. So these two things are not equal. So you have to be very careful about commutativity aspect of the matrix. Similarly, additive aspect is fine. You have if it is minus here, it will be minus here. Now note again, we have the product also works out, but you have to be careful about that the commutativity does not works out. What do you mean by commutativity? That means AB is not same as BA, right? So this is going to be A dB by dt. This is the matrix multiplication here, right here, plus dA by dt times dB, sorry, times B. But this is not equal to dB. Note that dA by dt times B is not equal to what? Not equal to B times dA by dt, right? So these two matrices are not equal, so therefore there cannot be other formula for the derivative. So you have to be careful about that part. So that takes care of the introduction. Now let's talk about linear independence and dependence of vectors, and uh, then we'll talk about linear independence and dependence of the solutions, right? Because after all, our goal is, if you're given a homogeneous system of differential equation, how to produce the fundamental set, right? So consider the k vectors x1, x2, xk. They are linearly dependent if there exists non-zero if there exists constants c1 to ck, not all zero. Yeah, some of them can be zero, not all zero, such that c1 x1. So I'll use an arrow on top because there's no distinguishment of the boldface and non-boldface here, plus c2 cn. Okay, there are k of these, so k zero, such that this happens. Yeah. Otherwise, we call them what? Otherwise, if there are no such non-zeros, if none of them are non-zero, that means everyone is zero, right? So otherwise they are called linearly dependent, independent. Yeah, so linearly independent solutions are the solutions we seek, right? So let's look at an example. So suppose you have x 1 bar 1 2, say 1 1 1, x 2 is 1 1 minus 1, x 3 3 3 minus 1. Then these vectors are linearly dependent. Why is that? Since you can see that x1 plus 2 x2 minus x3 equals to 0. So since these add up to 0, we get what? That they are linearly dependent. Yeah. Now, if you consider now consider example 2, example 1. Consider the following. These are you would have seen them as standard bases for R3. Then we have what? Then you can see that if you take C1 times 1 0 0 plus C2 times 0 1 0 plus C3 times 0 0 equals to 0 0 0, this implies that C1 equals to C2 equals to C3, and all of them are 0. So therefore, what? They are linearly independent. They are linearly independent, right? So now we need a methodological way of determining this. Yeah. How to determine this? Independence or dependence. Yeah. How to determine linear independence or dependence. Okay, so that's the question. So let's embark on that. So there's a relationship between determinants and linear independence. So given set of k vectors, x1, x2, xk, we can concatenate them to form a matrix and then use resulting matrix to determine if the vectors are linearly independent. So already your xi's, these matrices belong to what? they are 1 cross, say, you can say that they are n cross k cross 1 vectors. Okay, so the dimension should match, all right? So you start with set of k vectors where each of the vectors are k cross 1 vectors, then we concatenate to form this and then check whether they are linearly independent or not. So given, you start with, say, given these, we can construct, so given these k vectors, construct. So what is the concatenation will look like? The concatenation will look like so basically arrange them one after each in the as the columns. Then C1x1 plus CKxk is same as you take this matrix X and you are finding C1 CK, and this can be seen as XC, right? Where C equals to CK. Now, if you recall from linear algebra, now the only solution, so XC equals to 0, that is same as 0, 0, 0, K times K cross 1. So this is equal to 0 has a unique solution, has a unique solution C1 CK equals to 0, 0, 0, only if what? Only if what? Only if determinant of this new matrix formed X is non-zero. Yeah. So you're solving XC equals to 0 and you want to see whether, so it will get only C1, C2, Ck equals to 0 only if determinant of X is non-zero. Yeah. So let's write this down. So the only solution XC equals to 0 is C equals to 0 would give mean what? Mean few things. Mean what? That X are linearly independent. That is if and only if X is non-singular. That is determinant of X is not 0. So this is how we can decide, right, the linear independence. Okay. So now the same thing. So again, our goal here is to understand system of first order differential equations, which we saw in the last class, we converted it into matrix form. So now suppose so we want to understand the solutions to that system of differential equations. They will also be a vector. So let X 1, x2, xk be the vector functions of variable t on some interval I. Now we want to discuss the linear independence and the linear dependence of this, right? So we say that these vectors are linearly dependent on I if there exists a constant C1, C2, Ck independent of I. Now this is the important part. We'll digress that in a minute, such that you get C1 equals to 0 for all t belonging to I. Yeah. So, or not all 0. Okay. So exists constant, not all 0. So not that all of these constants C1, C2, Ck are 0. Okay. But this happens. Otherwise, we call them linearly independent. Yeah. Now remark, linear independent vectors do not need to be linearly independent vectors for every fixed t in I. Yeah, they can be linearly dependent for each point in I, but with different constants for each value. Okay. Conversely, linear independent vector always yield a linear independent vectors for each of the fixed t. So consider the following scenario. This is an important eye-opener problem. So suppose you have this vectors te to the t, te to the t, x2 is 1t. So these vectors are linearly independent, but for any fixed value of t, x1t and x2t are linearly dependent. Okay, so let's digress that. Let's look at that a bit. So we have x, right, e to the t, t, e to the t, 1t. Now what is determinant of this guy? So determinant of x is t e to the power t minus t e to the power t, which is 0, right? That means what? That means for every fixed t, for a fixed value of t, t, x1 and x2 are linearly dependent. So for fixed value of this is linearly dependent because you can see the determinant for any fixed value of these, you'll get matrices dependent, right? However, note that if you look at C1x plus C2 equals to 0, this gives us what? 0 as basically as a vector 0. Okay, so this gives us e to the power t, t to the power t, c, c1, c2 plus c2, 1 plus this has to be c1 plus c2 equals to 0. Equals to 0, right? Now for no values of this, so we want to basically see the following. So what values of C1 and C2 we get, right? So so for example, if you look at t equals to 0, then you get what? Then you get C1 e to the power 0 plus C2 equals to 0, which gives me C1 equals to minus C2. And if t equals to ln 2, I get what? We get for the first part, we get C1 ln 2, so it's going to be 2C1 plus C2 equals to 0, which gives me what C1 equals to minus half C2. So you see, you don't get a fixed set of values really, right? So for dependence, these constants must be independent of, that's funny to say that, these constants need to be independent of T. What is the upshot of this discussion? That these two guys, these two vectors are linearly independent, all right? Because there's no fixed constant C1 and C2 which you add, you get 0, except for C1 and C2 both 0. So the linear dependence or independence differs in the cases of functions uh, than the cases of vector with fixed real values or complex values, but fixed values. So let's discuss, our next part is discussion about eigenvalues and eigenvectors. So let A be an n cross n matrix. An eigenvalue of a matrix A is a scalar lambda such that Ax equals to lambda x for some non-zero vector x. In that case, we call lambda to be eigenvalue and x to be an eigenvector corresponding to the eigenvalue lambda. Now, what is the motivation behind it? You can think about it as, well, one way to think about it is that in the direction of x, vector x, your matrix multiplication is as if you're scaling the vector in that direction by lambda, right? So now how do you find out the eigenvalues? So eigenvalues are solutions to the characteristic equation determinant of A minus lambda I equals to 0, right? You basically get from here, you get A x is same as lambda times I x, where I is n cross n identity matrix. So we have A minus lambda I x must be 0, right? So this is a vector. That means what? Determinant of this matrix must be 0. Okay. So note that this is the polynomial of degree n in lambda. Now let's do the following example. Find the eigenvalues and eigenvectors of the following matrix. So again, it's a square matrix, so this can be done. So we have A minus lambda I. So what is A minus lambda I? This is going to be 1, 4, 1 minus 2 minus lambda times I, which is identity matrix, 2 cross 2 identity matrix. So when you do this subtraction, you get 1 minus lambda, 1, 4, minus 2 minus lambda. Yeah. So determinant of A minus lambda I is going to be 1 minus lambda times minus 2 minus lambda minus 4 times 1. This is going to be lambda minus 2 lambda. So this is going to be lambda times lambda, lambda square plus lambda minus 2 minus 4, which is going to be lambda square plus lambda minus 6. And that give me lambda plus 3 times lambda minus 2 equals to 0. So therefore, determinant of A minus lambda I equal to 0 would give me what? Lambda is equal to minus 3 or lambda is equal to 2. Okay, so these are the eigenvalues. Now we want to construct the eigenvectors. So find eigenvectors. So these are the eigenvalues, right? So Eigen Values. Now we need to find out eigenvectors. So first corresponding to lambda equals to -3. Then we'll have what? A x equals to -3x, or we want to write a vector in this format, or we get a minus, so minus will become plus, so plus 3i x equals to 0. So now we need to solve for x which satisfies this. So let's see. We have a plus 3 is going to be adding 3 in this part and 3 in this part. So we get what? Therefore, this system becomes 4, 4, 1, 1 times x1, x2 equals to 0, 0. Right? Because a plus a is a plus 3i. Let me just write that here. A plus 3i equals to what? A is 1, 4, 1 minus 2. 3i is 3 times 1, 0, 1, 1, 0, 0. Now add 1 plus 3, which is 4. 1 plus 0, which is 1. 4 plus 0 is 4 plus 0 is 4. And we have minus 2 plus 3, which will give me 1. Okay. So I get this equals to 0, 0. So this gives me what? This gives me x1, 4x1 plus 4x2 equals to 0. x1 plus x2 equals to 0. These are essentially the same equations, right? Multiple of each other. So this gives me x1 equals to minus x2. And in that case, what my eigenvector is going to be? My eigenvector is going to be x equals to, instead of x1, I'll write x1, instead of x1, I'll write minus x2. x2 will remain as it is. This is minus, or that matter, x2 times minus 1, 1, right? Or constant times minus 1. So this is your eigenvector corresponding to lambda equals to -3. Yeah, where c is non-zero. Yeah, it's any non-zero, any. Similarly, you can find out for lambda, so similar calculations. Lambda equals to 2. Okay. Now, for any given eigenvalue, it is always the case that there's infinite family of eigenvectors. Right? I mean, like, because as you keep changing C, you will get infinite family of eigenvectors. In fact, they form a vector subspace. If you arrange, if you use 0 with them as well. Okay. So generally, there's an infinite family of eigenvectors. So we'll normally pick one, the non-zero value of C. We might choose C such that has simple form. For example, in this earlier case, we could choose C to be 1. So in that case, we got eigenvector in the previous case as so we could have chosen corresponding to C equals to 1. And in that case, we call the first eigenvector could have been what? 1 minus 1. Yeah. Yeah. Corresponding to lambda 1 equals to -3. Now let's do the computation for lambda equals to 2. Again, we have A minus 2i x equals to 0. So we need to find out what this vector could be. So again, we have 4, 1. So what is the original matrix? A is 1, 1, 4, minus 2, minus 2 times I, which is 1, 1, 0, 0, and x equals to 0. Yeah, this is what it means. So we get what in this case we have minus 1, 4, 1, minus 4 times x1, x2. So I'm gonna write the augmented matrix now, 0, 0, right? So you can solve it using augmented matrix. So now this is, if you row reduce it, you get so add first row, so subtract R2 plus R1 goes to R2. In that case, this will become 0, 0, minus 1, 4, 0, 0. This implies what? Minus x1 plus 4x2 equals to 0. This gives me x1 equals to 4x2. This would imply what? We have x1 as 4x2 and x2 as x2. As your vector x, or in other words, your eigenvector corresponding to vector corresponding to lambda equals to 2 is given by constant c times 4, 1. Okay. So this is your x2, or in other words, or with c equals to 1, we have x2 equals to 4. So note that it's enough to list one non-zero vector as an or only the bases of the eigenspace. Yeah. So we'll occasionally see a 3 by 3 matrix and larger system. However, we'll focus on 2 by 2 matrix and corresponding 2 by 2 system of differential equations. All right. So our restriction is 2 by 2. It is important to understand how the eigenvalues and resulting eigenvectors behave. That will decide how the system will look like. Okay. Now, consider so now we want to discuss very briefly about eigenvalues and eigenvectors of 2 by 2 matrix. So consider 2 by 2 matrix. Since characteristic equation is a polynomial of degree 2, there are two cases for lambdas, right? Because lambdas, the eigenvalues are solution to the characteristic equation. What is the characteristic equation? Determinant of a minus lambda I. This polynomial is called characteristic equation. Now, if two eigenvalues are distinct, then we have each eigenvalue has one eigenvector x1 and x2 up to a constant. Means the eigenvectors are same up to a constant. Yeah. What do I mean by that? Let me digress. That means eigenvector corresponding to lambda 1 will be exactly one vector, and similarly eigenvector corresponding to lambda 2 would be a different vector. And they are all within, for the given eigenvalue, you will have the same eigenvector. As you see here, say for example, eigenvector corresponding to lambda equals to 2. They are all multiples of 4, 1. So it's unique up to the multiplication by constant. So now the other case is basically you can have a repeated eigenvalues. That means there is at least one normalized vector However, we may not be able to, there may not be a second linearly independent eigenvector. So we'll work these cases out. So now case 2 can lead to complications in solving or ODEs, system of ODEs actually, as we saw earlier, when there are repeated roots of the characteristic equation of the homogeneous second order differential equation. So we'll come to that case when we are looking at that problem. So let's look at the following. Find eigenvalues and eigenvectors of the matrix where A is a real constant. So again, I will quickly form the matrix, the characteristic equation. So let's look at that determinant of A minus lambda I. This is going to be determinant of lambda minus 1, 1 minus lambda, A minus 0. So that's fine. 0, 1 minus lambda, 0, which is 1 minus lambda square. So now lambda equals to 1 is the eigenvalue. So now let's find the corresponding eigenvectors. Eigenvector for lambda equals to 1. So we need to solve for A minus lambda I times x equals to 0. That is, A minus lambda I is going to be 0, A, 0, 0 times x equals to, on one hand, this is going to be A, your x is of form x1, x2. Now, this is 0, 0, then there are two cases really, right? Case 1, if A is not 0, or A is rather take the easier case first, when A is equal to 0, then what will happen? Then you'll get this equals to 0. So any x1, in that case, any x is an eigenvector. In that case, the eigenspace is of dimension 2, and you'll get these are your 1, 0, and x2 are eigenvectors. However, if case 2, if A is non-zero, then we get what? Then we have ax2 equals to 0. This implies x2 equals to 0. And that would give us we'll have what we'll have x1 0, that is going to be c times 1 0 are eigen vectors. So the idea is there's only one linearly independent eigenvector. So why are we discussing this? We are discussing this because in the end, we want to find out fundamental set of solutions, and they will correspond to the linearly independent vectors of functions which satisfy the system of Ds. We'll see more of this in the next class. Thank you for your attention.